Hello everyone, I'm Akash. In today's video, we will solve another interesting question on group theory which I have posted on our YouTube channel community post on 2nd May. The question is, consider the following statements. We have given two statements, statement A and statement B. And from options, we can see that we need to verify whether these statements are true or false. So let's verify one by one statements. Statement A is if G is an infinite abelian group, then it has at least one element of infinite order. Is this a true statement? No. Statement A is false. To see this, consider G be a power set of X equipped with operation symmetric difference, where X is any infinite set. Okay. The operation symmetric difference is given by for A comma B belongs to G as A and B belongs to G. That means that A and B are element of power set of X. And that means that A and B are subsets of this set X. So A and B belongs to G. That means that A and B are subset of X. So for A comma B subset of X, A symmetric difference B is defined as A minus B union B minus A. That is complement of B in A union complement of A in B. This is the definition of asymmetric difference B. Now, I will give one task. Task first. Verify that the set G with operation symmetric difference is group. You need to verify whether the set G satisfy all four group axioms with respect to this operation or not. That means you need to verify whether G is closed with respect to this operation is associative or not. There exists an identity element in G or not. You need to also verify that every element of G has inverse or not. Okay, if you verify that all these four axioms satisfies, then G will become group. And the answer is the G is group. Just you need to verify these all four axioms. Now, consider asymmetric difference B. By definition, asymmetric difference B is A minus B union B minus A, and which can be written as B minus A union A minus B. Okay, and this is nothing but B symmetric difference A. So for any two element of G, we see that A symmetric difference B is equals to B symmetric difference A. So this implies G is an abelian group. And as X is an infinite set, so power set of X contains infinite number of elements, hence consequently G is an infinite group. So G is an example of infinite abelian group. Now we need to check whether it has at least one element of infinite order or not. Now for any arbitrary element A belongs to G, consider asymmetric difference A. What is asymmetric difference A by definition? A minus A union A minus A, which is nothing but phi union phi, that is nothing but empty set. So we see that 2 is the least positive integer such that asymmetric difference A is equals to the empty set, that is identity of G. So this implies order of A is 2. But A is any arbitrary element of G. So from here we see that every non-identity element of G has order 2, and the identity element, which is nothing but phi, has order 1. So from here we see that every element of G is of finite order. So there does not exist an element of infinite order. So here we found an example of infinite abelian group which does not have an element of infinite order. So the statement A is false statement. Can we have another example for A? Yes. For example, consider G is equals to set of complex number Z such that Z to the power n equals to 1 for some n belongs to positive integer. It is a set of all roots of unity. That is, it contains all first root of unities, all second roots of unities, all third roots of unities, and so on. You can verify that this set form a group under the operation multiplication of complex numbers, and it is an infinite abelian group, and every element of this group has finite order. So this also serves the counter example for statement. So from these two examples, the first example is the power set of x equipped with operation symmetric difference where x is in any infinite set, and the second example is this. Both by both of these example, we have the statement A is false. That is, if G has infinite abelian group, then it has at least one element of infinite order? No, not necessarily. As we can see that these two groups are infinite abelian groups, but they do not have at least one element of infinite order. So the statement A is false. Now, let's verify the statement B. There exists an infinite non-abelian group having infinite abelian subgroup. Yes, for example, take G is equals to cyclic group Z direct product S3. Okay, S3 is a symmetric group on 3 symbol. It is a famous example of non-abelian group, and it is a cyclic group, and hence it is abelian. So their direct product is again a non-abelian. Since we know that the direct product of groups is abelian group if both of the factors are abelian. But here one factor is abelian and another factor is non-abelian. So overall this direct product, that is G, is non-abelian group. So, and as Z has infinite number of elements, so G has infinite number of elements. So it is an example of infinite non-abelian group. Now let's check whether it has infinite abelian subgroup. Yes. To see this, consider H, which is equals to Z direct product trivial group. Then clearly, as Z subgroup of Z itself and trivial group subgroup of S3, so H is a subgroup of G. And as Z contains infinite number of elements, so H contains infinite number of elements. Moreover, this H isomorphic to Z with respect to addition, and we know that Z with respect to addition is cyclic group, hence abelian group. So overall H is infinite abelian subgroup of G. So there exists an infinite non-abelian group which has infinite abelian subgroup. So the statement B is true statement. So the correct option is statement A is false and the statement B is true. So the option 2 is correct. So in this video, I have given two tasks for you. First task is verify that power set of X with operation symmetric difference where X is any infinite set forms a group. You need to verify this set forms a group with respect to this operation. Okay, for that you need to verify all 4 group axioms, and the second task is that this set, that is set of all roots of unity under the operation of multiplication of complex numbers form a group, and also verify that it is an infinite abelian group, and verify that every element of this group has finite order. So these are two tasks for you. So if you found this video interesting and helpful, then please like and share this video and subscribe to our YouTube channel. Thank you for watching.